So yesterday's session focused, I would say, practically entirely, right, on these two charts over here, where we took some randomized data based on a known relationship, F, explaining the dependencies of Y on X. And then we considered three models. A linear regression, that's your orange, that's your linear relationship, which does a pretty bad job of fitting the data. After all, it would look cubic or maybe higher order. In fact, we did take a cubic curve yesterday, as you remember from Desmos. We have the blue curve and the green curve. So each curve in this context is a model. We have these three models, and we're benchmarking them against each other by calculating their mean square error. If you noticed my messages on the chat earlier today, besides the mean square error, there is also the root mean square error, which is in fact, I sent you a link to a specific Kaggle competition going back 2-3 years, where the winning team, the ranking was set depending on this root mean square error. You could actually get a very good idea, and it might be one of those things that we look into at some point. If the root mean square error was, I think, around 2000, you can actually get an idea of the winning team's predictions on average. You can sort of work backwards using subject of the formula. And we might even, we won't do it today. I'd like to press on the theory, but this is something that perhaps one of this week's sessions could actually explore at some point. So we're going to start reading, and probably this seems to be a good spot. So in this example, and we're referring to the back curve over here, we know the true function f, and do remember, it will never be the case in practice you don't know the function. That's the whole point of using data and fitting a model to the data available. And so we can also compute the test mean squared error over a very large test set as a function of flexibility. What are we saying over here? So there's the training and the test, mean square errors. Oh, right. I think what we're saying is, given that we know the true function f, you can very easily simulate, for instance, 100,000 observables that were not used in modeling the relationship between y and x. This is what we mean by a very large test set. We don't need to send out surveys. We don't need to interview people. We can just create the data ourselves based on f and the error term, right? Of course, in general, f is unknown. This is what we've just said, so this would not be possible. The test mean square error is displayed using the red curve in the right-hand panel of figure 2.9. This is what we're referring to. So we're calculating the mean square error for each model twice, once on the training data. And the training data is exactly what we're seeing over here. It's those points that we generated in Excel yesterday, we were using blue for the points. Each point represents an observable, in this case, an x comma y, although do keep in mind that in multivariate modeling, although the y retains one value, your input could have hundreds of different values, each one quantifying a specific feature, a specific characteristic of the observable that the model is using, of each observable, where we usually use n to represent lowercase n, or even uppercase. In fact, in that Kaggle screenshot that I sent, the formula was using uppercase n, just in terms of notation. The gray curve is the mean square error based on the training data. And the red is on test data. You would ideally use test data. What's the difference? Yesterday we said data is data. The difference is that the test data hasn't been used to actually fit these models. The test MSE is displayed using the red curve. As with the training MSE, the test MSE initially declines, initially decreases, as the level of flexibility increases. The level of flexibility. So for example, you're going from a linear model to a quadratic model or a cubic model, so it decreases. However, at some point, the test MSE levels off, you've reached your minimum, and then starts to increase again. This would be due to overfitting. Consequently, the orange and green curves both have high test MSE. So the orange and the green, to a certain extent, you can think of them as being at opposite ends of the spectrum. The orange just passes a straight line. All lines are straight. Whereas the green does its best to follow each data point. So it has its gradient is switching quite regularly from negative to positive, positive to negative, negative to positive. Whereas the blue is kind of that sweet spot where it's flexible, but it's not trusting the raw data. It's not trying to reflect the specific. It's trying not to go too far and reflect every single detail of the raw data. The blue curve minimizes the test MSE, and remember that's what we're after, which should not be surprising given that visually it appears to estimate F the best in the left-hand panel. So in fact, the blue is very close to the black. We're then going to include an error term. But look how close the blue is to the black curve. And that's what we're saying over here. The horizontal dashed line. Now, this is something we haven't discussed yet. Indicates, now we have this over here. Var epsilon, the irreducible error in 2.3. Let's take a step back. What is epsilon? Epsilon is our error term. Now, we do realize that we may have limited or next to no experience with random variables. Although it's written like a constant, although it's written like, so if this is quadratic, so think of if this was x squared, at first glance, if you're not familiar with the notation, this would appear that we're simply saying x squared plus 100. Whereas, in fact, it's not the case. This has a probability distribution, and each time we generate, for each observable that we generate, epsilon is going to take a different value. Now, the values that it takes on depend on the distribution, on the probability distribution. And yesterday we mentioned just coin toss, heads, tails. Heads has a 50% likelihood, tails has the other 50%. That's your probability distribution. Let's continue. So this dotted line means, do we remember in Excel, I entered two values in the top left corner. I don't think I saved that file from yesterday, so I'd have to do it again. But one of you asked, what does the 0.25 mean? The error term always has a mean of 0. So if you generate, and maybe we'll just see this in R. Just need to remember how to do it. I think it's R norm. Let's just check. What if I do 0, 1? Do I need to have a package installed? To my knowledge, if I type R uniform, I think we need to specify the number of, right, okay, very good. So your error term has a probability distribution. Now we can take a normal probability distribution. If you've ever seen histograms or, yes?
0 to run it.
No, it's not written as run if, or you should, it's written as run if, you mustn't read it as run if. What it is there are many distributions in probability. So for example, a coin toss, that's a uniform distribution. All outcomes have just, if each outcome has the same likelihood, that's a uniform distribution. So your bar chart at every possible outcome, we have the same probability. So that's a uniform distribution. So if we use 1 as heads and 2 as tails, just to give the numeric values, then this is a uniform distribution. It's a discrete uniform distribution in the sense that there are only a finite number of outcomes. It's not continuous. Now, the error term very often is not a uniform distribution, but what we call a normal distribution. I'm going to generate. We had, was it 100 data points yesterday? Let's stick to 100. I've generated 100 of them like this. One second. Why don't we make things easier? What if I take a binomial distribution? Just to give you an idea. Of let me have a look. So what have I done over here? Let's do it. Let's do it again. you need to think of these 100 values as each one representing either heads or tails. I've generated 100, either 0 or 1, and with a probability of 50%. Now, if I calculate the mean, so I can save these as a vector, so I could call them coin tosses. Now I can calculate the mean. And the mean is, as you would expect, close to 0.5. So roughly half of them are 0, and the other half, I think we can do this with table. This might work. Right, so out of these 100 simulations, 53 of them are tails, 47 of them are heads. But besides the mean, I could calculate as well the variance. And I'm going to explain what I mean by variance. But just to tie it in with this text, this is the variance. Notationally, if you have a random variable, so I can't say the variance of a curve, I can't say the variance of a pentagon, I can't say the variance of an equation, but I can quantify the variance of a random variable. And what do we mean by that? What we mean is how spread out the data is from the mean. So the mean is 0.47. And if I calculate the variance, let's see if this works. The variance is 0.25. The larger the variance is, the greater the variance is, the more, I'll phrase it differently. Let's put it this way. The greater the variance is, the more volatility you have in your data. So going back to these data points, if we increase the variance, then you're going to expect, on average, a greater distance from between the data point and the black curve. The black curve just gives you f of x. Then the error term, each time you generate the error term, and each observable will have a specific error term. It could be positive, it could be negative, it could be 0. If it's 0, it means that you just have f of x. So your data point will be exactly on the curve. The larger the variance, the more volatility you're going to see in your data. The more, I'm not doing a good job of explaining it, but I think we get the idea, or I hope we get the idea. Like I said, it would be more scattered. It would be, so the lower the variance, the closer, I think that's the best word, the closer to the black curve, these generated data points would end up. The higher the variance, the further away, on average, the further the data will be further away from the black curve. Okay. Now our error term very often is the normal distribution, and we can generate 100 of them. And yesterday we took a mean of 0 and the standard deviation. And standard deviation is the square root of the variance. The standard deviation of 0.75. So we can generate them. And why don't we just take 2 decimal places? Like this. And we can save them and yes,
The black curve is the actual or the estimate? The estimate, right?
the black curve is the actual. The black curve is the actual. The black curve in real life you won't have the black curve. The black curve is, I keep on using the word omnipotent, that we know everything. We know the relationship between y and x. In real life, you'll only have the data points. The larger the variance, the further away the data points would be from the black line, from the black curve, excuse me.
Thank you.
Okay. Let's call these our error terms. So I've saved it as error terms. It's these 100 values. We can calculate the mean. We're expecting it to be close to 0, close in inverted commas, of course. Mathematically, the word has little meaning. Closer does have a meaning because mathematics is all about comparing two numbers. And I can calculate the mean of the error terms. And look, that's close enough, right? It's negative 0.02. You can calculate the variance, and what I'm expecting is going to be 0.75 squared, if I remember my basic statistics. The variance of the error terms. Let's see, what if I square? So what if I need to square root it, right? Yeah, look, it's pretty close, isn't it? So when we took 0.75 yesterday, when we took 0.75, we decided at the outset, remember, we were playing God. We decided that besides the black curve explaining the relationship between y and x, we then needed to include an error term to capture the limitation of the model that inevitably isn't going to consider all the relevant variables. And we decided, let's give it a standard, let's give it, what did I take yesterday? Was it the standard error? Let's take a standard error of 0.75. And that's what's giving you, if you will never have a standard error of 0. And in fact, what if I do 0? Do you get an error? I'm curious. See, if the standard error is 0, let's take a mean of 100. Let's take a mean of 100. Let's take a mean of, let's take people's height, a mean of 180 centimeters. Look, there is no variability within the data. You're not going to do statistics over here. Everything, it's perfectly homogeneous. Every data point, if we're looking at individuals, everyone over here is 180 centimeters tall. There is no uncertainty. There is nothing to forecast. It's like saying the mass of the moon. But that's just a constant usually. Right, yes, it could change, but you would typically, you're not going to take it as a function of how many people live on Earth or a function of some other variable. So statistics, these random variables that we're so fond of in statistics, and I've taken a normal distribution. If the variability is 0, if the standard deviation is 0, your histogram to take a secondary school concept, would just be like this. One single bar at 180. there is no variability. There really is nothing to discuss, is there? If this data is reflective of the larger population data, if every data subject out there has their Y component as 180, 100%, you could set this at 100%, then there is no statistics to discuss. The statistics comes into play when you have variability. And that would be one of the widely used distributions is the normal distribution. You may have heard of it as the bell curve. It comes up it's I guess we could say ubiquitous. It really is. So it's like this, and I need to mirror it. It's symmetric about its mean. The great thing is that its mean, median, and mode are all the same value. You get the picture. I need to keep on going on. Visually, I need to keep on drawing. Now, the greater your variance, the more widely spread out this data would be. So let me give you an example. So let's take a standard deviation of 1. We have these error terms. And for example, we could ask the maximum and the minimum. What is the max of the error terms? It's 182. What is the minimum of the error terms? It's 177. So that's your greatest data point and your smallest data point or data value. If I take a larger variance, there's going to be more variability. So now it's between 184 and 175. And what the authors have done over here is that instead of taking I picked 0.75 yesterday, they have picked for the variability of their error term, they have picked 1. Yeah, so they picked 1. In fact, if a normal distribution has a mean of 0 and a standard deviation of 1, which is what the authors have taken over here, we don't refer to it as a normal distribution, but we refer to it as a standard normal distribution. It's not too important, but I'm just putting that out there. And they're speaking of irreducible error. The irreducible error is this. So when you're calculating the error between the actual data, the actual output, we're trying to predict Y, the Y variable, height, wages, you name it, against the model's predicted outputs. This error can never be entirely eliminated, which is why we're referring to it as the irreducible error. And remember, it stems from the fact that your model, one of the primary reasons at any rate, is that your model isn't allowing for every single variable that may influence the output variable. It is a simplification, and this is a phrase that we're going to use on a regular basis. The model is a simplification of reality. If in reality there are 1,000 factors that influence to some extent or another an output, what you would usually do is that your model, you would only want to find, for the sake of simplicity, you would only want the most relevant factors. For example, if there are 1,000 factors, maybe it's only enough to find 20 of them that will predict that give you a prediction that is within 90% of the actual. And it's a trade-off, isn't it? Many modelers would be more than willing to discard the vast majority of input variables if their impact is minimal. And look at this, look at this. Your mean squared error, maybe it's the case that it can never really go below the irreducible error. I'm not entirely sure if that's the case. There might be some results in this book that may prove it from a theoretical standpoint. But either way, it should make intuitive sense to you that we cannot go much below the error, the variability within the error term. The horizontal dashed line indicates var epsilon, so the variability within the random variable that describes the error term. Yesterday we took 0.75, which corresponds to the lowest achievable test mean square error among all possible methods. So this is as low as we can. The error terms, have I been referring to it as variability? That's not wrong, but strictly speaking, I should call it variance. You can think of them as interchangeable, though. The error term's variance, the uncertainty that the error term contributes to our predicted y hat, is the lowest value of the mean square error that you can hope to achieve. Hence, the smoothing spline, represented by the blue curve, is close to optimal. This curve over here, the blue, is really as close as you can get when it comes to reducing your model's mean square error. So not only is it better than the orange and the blue, wrong, not only is the blue's mean square error lower than the orange and the green, but it's practically as low as it gets, which is what we mean by as close to optimal. In the right-hand panel, so referring to this again, as the flexibility of the statistical learning method increases, by flexibility, we mean linear is the least flexible. And the green one was the most flexible. It practically followed the data down to each change from one data point to another point. As the flexibility of the statistical learning method increases, we observe a monotone decrease in the training MSE, but a U-shape in the test MSE. Monotone, it is always decreasing, mono, 1. Whereas this is a U-shape, this is not monotone, it's decreasing, but then it increases again. And apparently they've measured flexibility. Don't ask me what this measurement or how this measurement has been calculated. I do know flexibility is how much we're allowed to sort of bend and follow the data. So this is the trade-off. The green has the highest flexibility, but then it has, then what you pay is that you get a higher mean square error. This is a fundamental property of statistical learning that holds regardless of the particular data set at hand and regardless of the statistical method being used. Okay. As model flexibility increases, training mean square error will decrease, which stands to reason. You're following the data that you use to create the model. But the test MSE, based on test data, based on data that has not been used when designing the model, may not. When a given method yields a small training MSE, but a large test MSE, we are said to be overfitting the data. This happens because our statistical learning procedure is working too hard to find patterns in the training data and maybe picking up some patterns that are just caused by random chance rather than by true properties of the unknown function f. So imagine it's a coin toss experiment and you, just by sheer random chance, get 100 consecutive heads. If you're overfitting, then your model will start thinking that you should expect maybe at a higher rate than is in fact the case, situations where you will get 100 heads because you are putting too much reliance on the data that you're using. When we overfit the training data, the test MSE will be very large, and that's what you want to avoid, because the supposed patterns that the method found in the training data simply don't exist in the test data. You have placed too much faith in the training data. Note that regardless of whether or not overfitting has occurred, we almost always expect the training MSE to be smaller than the test MSE, because most statistical learning methods, either directly or indirectly, seek to minimize the training MSE. Overfitting refers specifically to the case in which a less flexible model would have yielded a smaller test MSE. So when do we say that we have overfitting? The green is said to be overfitted. The green is said to be overfitted. This green model is overfitted since we have managed with the blue model to obtain a lower MSE using a less flexible model. This has like flexibility 5. This has flexibility, whatever, 22. Although the scale, never mind, it's not important, is it? So that's when we would describe a model as having overfit the data. Figure 2.10 provides, and this is what I love about this book, there's so much repetition. Not only that, but this chapter is really setting up the main ideas that we're going to be discussing in each subsequent chapter. Figure 2.10 provides another example in which the true f is approximately linear. Right, so in this case, our true f is approximately linear. Again, we observe that the training MSE decreases monotonically, the training is the gray. So again, we'll fit three models. A linear model, the blue is, I don't know what kind of model, and the green is what we're referring to as an overfit model. However, because the truth is close to linear, the test MSE only decreases slightly before increasing again. This time round, there isn't such a discrepancy in MSEs, in test MSEs between the two models, because the data, the true function is linear in nature. Okay. I am skipping occasionally one or two sentences. In practice, one can usually compute the training MSE with relative ease, of course, because you already the training MSE is based on data that you definitely have. It's the data that you used to design the model in the first place. But estimating test MSE is considerably more difficult because usually no test data are available. This is definitely true in insurance. So a lot of the work I do is based on what in general insurance. So general insurance is non-life. It is, the US terminology is property and casualty. So think of motor insurance, workers' compensation, third-party liability, cyber insurance. And what we use is data that's structured as a triangle. Definitely one of those things that we'll be doing in a future session. But besides the training triangles, we have no test triangles. Not at the time of design. Obviously, as time goes by, then you can see how good your forecasts were. But it's not something that we can perform after having right after designing the model. We can never go in front of the reserving committee or the board and tell them, we've designed this model and this is the test MSE. We just don't have that data to perform that calculation. As the previous three examples illustrate, the flexibility level corresponding to the model with the minimal test MSE can vary considerably among datasets. Throughout this book, we discuss a variety of approaches that can be used in practice to estimate this minimum point, okay, the lowest MSE. One important method is cross-validation. If you've ever come across, there's a website. It's massive in just the tech world, but not just the tech world. It's called, is it called Stack Overflow? But there's also Math Overflow, Italian Overflow. There's just the topics are quite varied. The data science sort of sub overflow is called either cross-validation or a similar name, which is a method for estimating test MSE using the training data. Interesting. I have absolutely no experience of this. So it'll be really interesting to see what we're going to cover when we get to that chapter. New section. The U-shape observed in the test MSE curves turns out to be the result of two competing properties, which is why we're speaking of a trade-off over here, of statistical learning methods. Though the mathematical proof is beyond the scope of this book, it is possible to show that the expected test MSE for a given value x0 can always be decomposed into the sum of three fundamental quantities: the variance of f hat of x naught, the square bias of f hat of x naught, and the variance of the error terms. I'm not familiar with this formula, but this is expectation. This is what you would expect. Here, the notation E of this defines the expected test MSE. I think we can safely skip the mathematics of this section. Equation 2.7, but let's see if we can at least get a heuristic understanding. Equation 2.7 tells us that in order to minimize the expected test error, we need to select a statistical learning method, f hat, that simultaneously achieves low variance and low bias. Note that variance is inherently a non-negative quantity. Variance will always be non-negative. For instance, if I go into R and I try giving it a negative variance, when we say variance and standard deviation, they're practically the same thing. Although maybe for standard deviation, yeah, it didn't work, in fact. Look, we just got NAs because it can't handle a negative variance. Variance is always positive. Variance is inherently a non-negative quantity. Square bias is also non-negative, so there's a point of squaring it. Hence, we see that the expected test MSE can never lie below the variance of E, right? The lowest that you can get for these two terms is 0, which means that you can't get a negative to zeroize the final term. What do we mean by the variance and the bias of a statistical learning method? Variance refers to the amount by which f hat would change if we estimated it using a different training data set. Since the training data are used to fit the statistical learning method, different training data sets will result in a different f hat, right? This stands to reason, depending on the data that you're using, well, that's going to directly impact the f hat that you are building over here. F hat is the model, but ideally the estimate for f should not vary too much between training data, right? That's what this is what we would want, right? That when you take your training data, if you've surveyed, I don't know, 1,000 people, that surveying a different group of 1,000 people isn't going to give you a significantly different model. However, if a method has high variance, then small changes in the training data can result in large changes in f hat. And I think the point is that really you need to pick input variables that have such a large influence on the output that your error term isn't going to be too large. But right now we're looking at the variance of the model itself. So far we've been discussing the variance of the error term. But now there's the variance of the model. I know there's a lot to digest over here, but we have the variability of the error term. That's kind of like how scattered the points are below and above, how far they are from the true relationship. Now we have the variance of the model itself. However, if a method has high variance, then small changes in the training data, this is what you don't want in practice, can result, although sometimes it's unavoidable, can result in large changes in f hat. In general, more flexible statistical methods have higher variance, and you would expect that, right? Let's see if we have a diagram. No, but we'll have to go back up. Consider the green and orange curves in figure 2.9. So the green and the orange. If I moved one of these data points, it's not going to make a big difference, right? To the orange. If I delete this data point, if I delete it, and I place it over here, are you expecting a significant change in the intercept and the slope of this line? I would say intuitively, I wouldn't. But look at the green curve. Wouldn't the green curve, just the way it seems to be following the data, wouldn't it probably have a much higher local maximum over here? Maybe we'll do something like that. Or who knows, maybe we'll go all the way till there and then come back down. Now that's significant. Just a single data point has had an a disproportionate effect. It's just one data point, a disproportionate effect on the curve that we're fitting. So green is the overfitted, orange is the linear. The flexible green curve is following the observations very closely. It has high variance because changing any, and great, that's exactly what the book is doing. Because changing any one of these data points may cause the estimate f hat to change considerably. In contrast, the orange least squares line is relatively inflexible and has low variance, because moving any single observation will likely cause only a small shift in the position of the line. On the other hand, bias refers to the error that is introduced by approximating a real-life problem, which may be extremely complicated, by a much simpler model. For example, linear regression assumes that there is a linear relationship between y and these p input variables. It is unlikely that any real-life problem truly has such a simple linear relationship, and so performing linear regression will undoubtedly result in some bias in the estimate of f. In figure 2.1, and this is figure 2.1, the true f is substantially non-linear. The true f, the black one. So no matter how many training observations we are given, it will not be possible to produce an accurate estimate using linear regression. In other words, linear regression results in high bias in this example. However, in figure 2.10, the figure f is very close to linear. And so given enough data, it should be possible for linear regression to produce an accurate estimate. Generally, more flexible methods result in less bias. As a general rule, as we use more flexible methods, the variance will increase and the bias will decrease. The relative rate of change of these two quantities determines whether the test MSE increases or decreases. As we increase the flexibility of a class of methods, the bias tends to initially decrease faster than the variance increases. So remember, it's this balancing act. It's this balancing act. So this might decrease slightly, but this might increase a lot. Wait, let's do it this way. The variance, you might manage to decrease the variance by, I don't know, 50%, but the bias only increases by 25%. So that means overall, the MSC has decreased. This is what they mean by the rate. The relative rate, you're comparing them. How are they changing relative to each other? The relative rate of change of these two quantities determines whether the test MSE increases or decreases. As we increase the flexibility of a class of methods, the bias tends to initially decrease faster than the variance increases. Consequently, the expected test MSE declines. However, at some point, increasing flexibility has little impact on the bias, but starts to significantly increase the variance. When this happens, the test MSE increases. Note that we observe this pattern of decreasing test MSE followed by increasing test MSE in the right-hand panels, all these. Decreasing, increasing. Decreases, but only marginally increases. Decreases, only increases marginally. Because now the overfitting is actually still, the overfitting shouldn't call it overfitting, should we maybe in this case. It happens to follow very closely the true relationship. Again, please don't think that you should be understanding everything first time round. I feel a bit lost, and maybe this section, while the diagrams were, no, there's a new section, isn't there? I don't think we've seen any diagrams in this section yet. Look, we've placed them all next to each other. I think these were the previous ones, right? Ah, I think we've decomposed them. So didn't we have these red curves earlier? Now we've decomposed them into the squared bias and the variance and the dashed line. So if you add the blue with the, if you add the blue to the orange, you get the red. And in fact, where do you get the minimum? Really over here, when you have a low orange and a low blue. This is just, it's a really great book. Again, there's a lot to take in, but it's using a diagram to better explain what this formula is doing. So this is a result that we don't prove in the book. We're just going to have to take it in, good faith. And it's saying us that your this is test MSC. When you see Y naught and X naught, that's the data that hasn't been used. So the test MSE. That's made up of these three components. The variability, I keep on saying variability, I should really say variance, although you're probably more familiar with the word variability. Same thing, but the technical word is variance. Can we just get an idea, and we'll finish within the next few minutes. How much of chapter 2? We're how far off from finishing chapter 2? Quite far off. Although when it gets into R, I don't think we're going to spend, we'll probably be able to do quick work of these pages. What to expect next, and hopefully we'll do another session tomorrow, is I think the same kind of principles, but instead of regression, remember what regression is. When you're predicting a specific output, you're predicting those y-hats. Instead, it's a classification question. And the great thing is that these concepts apply to both settings, both regression and classification. So look, we have a very, very similar formula. I'll explain what this is doing. It's called an indicator. Really just gives you, it tells you if yes, it gives you 1. If no, it gives you 0. So what it's asking is, let's say that you have so many observations, and this is a classification question. So you are classifying a book, whether it's a book that should be classified in maybe you've defined a group of books enjoyed by adult teens. Adult teens makes absolutely no sense, right? It is well, what's that fiction called? What's that type of book called? Young teen, I think. And really it's just telling you, did you get it right or did you get it wrong? If you got it wrong, if the classification was a wrong one, you probably get a 0. Well, you want to minimize the MSC, right? So let's see. Anyway, this is something to do. And now we no longer have we're not fitting curves over here. We're not fitting a curve. Instead, we're trying to create a region. We're trying to distinguish between one group of data and the second group of data. And we kind of have this boundary line. So we're saying anything in the blue is going to be classified as blue. Now notice that the orange observations are incorrectly classified in this region, and the blue ones in the orange region are incorrectly classified as well. A simulated data set consisting of 100 observations in each two groups, indicated in blue and orange. The purple dashed line represents the Bayes decision boundary. But once we take care of classification, which, okay, there's quite a bit, but then there's going to be some relatively straightforward R code. And we've already discussed this, and a lot of this has been mentioned in yesterday's session, or that session we had done in summer. Let's stop here.